Hey everyone, welcome to the ISMIX webinar, Technology Behind Robotic Cardiac Surgery, Understanding the Hardware. Before we start the webinar today, just a housekeeping item or two. For your questions, please use the Q&A pod and not the chat room so that the presenters and the moderators can better see your questions and be able to answer them. This is an important thing. We have a number of panelists today, so please use that Q&A pod. This webinar is being recorded. It will be posted on the ISMIX website, ismix.org. And at this point, I will hand over the webinar to our president, Dr. Benares.
Welcome, everybody. I would also like to welcome you to this webinar. You see, ISMIX renews this history of webinar activities, which have been very successful in the past. Today, our robotic task force has chosen a very, very interesting topic. We have heard a lot about robotic surgery, and we want to see now today what is behind the scenes. We have an excellent faculty. We have two very important moderators, Gri Dahl, which is the vice president of ISMIX and an expert on hybrid surgery transcatheter techniques, and Johannes Bonatti, who is one of the pioneers of robotic surgery the last 25 years. I will hand it to you, Gri and Johannes, and all welcome to this scientific activity.
Sure. Thank you, Nikos. I would like to introduce our panel. Also, three very well-known robotic surgeons, Dr. Sam Balke from the University of Chicago, current president-elect of ISMIX, Dr. Bob Kiai from Sacramento, past ISMIX president, and Piotr Szulbowski from Warsaw in Poland. Okay, Gri, can I ask you to introduce the first speaker, please?
Yes, thank you. I want to introduce the first speaker, that is Andrew Orekop from Robotics, introduced in Carnegie Mellon University, Pittsburgh, and he's an engineer and expert on robotics for minimally invasive surgery.
Hello, everyone. Yeah, thanks for having me. Happy to be here. So I was asked to come here and talk a little bit about how robots in general work, and then maybe give a little bit more detail in the context of minimally invasive surgery. But I'll be trying to highlight why building robots is hard, in particular, as I'm speaking through these things. So pretty much any robotic system can be categorized in the following way. So we've got components that provide sensing of the environment the robot's in. We have some compute that's making sense of that sensing information, and then making a plan for how the robot is going to behave in the environment. And then the robot has some actuators that allow it to physically affect the environment that it's in. And then the sensing is then updating its sense of the environment, and it kind of goes back in a loop. And so pretty much any robotic system has these components, and really there's a hierarchy in which these three elements happen. So we can zoom in on one robot joint, and we'll see there's a encoder, which is providing the position and velocity of the motor. There's a motor driver, typically a microcontroller, that is then feeding electric currents to the motor and then controlling the speed. And then as an aside, we've also got a gearhead that's increasing the torque of that motor, but reducing its speed, because the physics of motors, they typically operate really well at high speeds, but not as well at high torques. And so we have this gearhead to give us that trade-off between speed and torque. So then we can zoom out a little bit to a single robot arm. Typically there's 6 degrees of freedom. They're controlling the position in space, XYZ position, so 3 numbers, and then XYZ orientation. So we've got 6 states that we're trying to control. So a robot arm that really has 6 or 7 degrees of freedom, 6 or 7 motors. And there's a control computer that's making plans for that robot arm based on some feedback, let's say from a camera or some other sensor. So we can zoom out even further to the operating room, and we've now got multiple robot arms and of course our console and robotic arm system. The robot arm would be receiving desired tool motions, as you all know, and then the computer would be running those desired tool motions through a kinematics and dynamics model of the components in the system. It's very important that that model be really well calibrated. And then that's generating motion plans that command the joints to execute that desired tool motion. Now the console itself is pretty much another robot. There's two kinematic chains here that are like robot arms. The encoders in those joints of the robot arms are measuring the angles of those joints. We feed that through a kinematic and dynamics model of the console, of the arms in the console, and that then computes a desired tool motion, which then gets fed back into the robot. So then how are we actually generating that tool motion? Typically this is done with electric motors. And over the past 50, 60 years, the power density of electric motors has really improved a lot. So robot arms are getting a lot lighter and more powerful. This is a plot of specific power, so power per kilogram. And this is a log plot here. So you can see over the past 60 years, 70 years, we've seen 2 orders of magnitude improvement in specific power for electric motors. And a lot of that's been driven by brushless motors and microcontroller electronics that have allowed us to make these motors more efficient over time. And then fun fact, they are, the specific power of electric motors is now more than mammalian muscles. Specific power isn't the only performance measure for an actuator, but I am pretty proud that we've gotten better than muscles on this specific performance measure. Now, so even though we've gotten a lot better on electric motor specific power and power density, once you get down to scales 6 millimeters, 8 millimeters in diameter, electric actuation really doesn't work anymore. And so when we're trying to operate at scales like minimally invasive surgery, there's just a need for remote actuation. We can't miniaturize motors down to that scale. And so what you'll typically see is wire rope cables. We can put our actuators outside of the patient, take up the space they need, route cables down to the smaller diameter to those small mechanisms that you all have seen that you've been using. Now with this remote cable actuation, another thing we can do is make snake-like robots. We can route these wire cables inside of an elastic structure. And you all have seen some of these commercial products that are now coming on the market that use this technology. And how this typically works, you've got a elastic structure. This is just one segment of a snake-like robot, some elastic structure. And then within that elastic structure, you route the wire ropes, which could be pull cables. You can also just route push rods that would be stiffer, that can push and pull. So as you pull and push on these actuation lines, you're creating circular shapes in these actuated segments. And so then you can have multiple of these actuated segments and create this kind of snake-like motion. So this is just one mechanical architecture for a snake-like robot. There are lots of other potential ways you can generate this type of snake-like motion. There's a picture of what's called a concentric tube robot with these telescoping pre-curved tubes. This is a similar concept with laser etched notches. This is a hyper-redundant robot that the current group I'm in works on that has these rigid links that lock and loosen, allowing you to follow kind of arbitrary curves in space, and these multi-backbone continuum robots too. And so these technologies are in varying stages of readiness for clinical deployment, but hope to see more of these being utilized in procedures in the future. So people always ask, why can't we go even smaller than we currently do? Challenge is as you reduce the diameter of one of these instruments, the strength of the materials just goes down. And that then affects the instrument life, as an example. Affects the reliability of the device. So you can only operate for so many cycles as you get down to those really small diameters, especially with respect to the wire ropes. And of course, as you go down in diameter, the stiffness goes down too. And so that affects the maximum force that we can apply on tissue with these tools. And then as the stiffness goes down, precision goes down too. You want your robot to be as rigid as possible so you can execute precise motions. As it gets floppier and floppier, your ability to do those precise motions goes down. So that's why we really can't, right now, can't go much smaller. Of course, we're always, as engineers, trying to manage these trade-offs depending on the application. But those are some of the challenges in terms of miniaturization. Yeah, and then one drawback of remote actuation I want to highlight is the transmission losses in the actuation. So you get some force from the actuator outside of the patient, and then we have these transmissions that bring those wire ropes to the instrument. And so within that transmission, there are these nonlinear losses, primarily related to friction, but also just mechanical clearances, heat losses, flexibility in the actuation lines and in the transmission. And those nonlinear losses are difficult to model, difficult to predict. They're a function of the state of the system, the velocity, even things like temperature and how long the tool's been used. And so this relationship between the force at the actuator and the force you're actually applying to the tissue is hard to know. It can be calibrated, but it's just a challenge. And so what that means is that it's hard to know precisely what force you're applying on the tissue. So if we want to provide some kind of safety for clinicians to prevent them from applying too high forces, it's difficult to do. And this is one reason why force feedback is challenging. Now you might say, well, can we just put a force sensor on the tip of the device? But force sensors are also very difficult to miniaturize, especially at those small scales. And then another thing I'd like to highlight is why force feedback is hard is the instabilities that can occur. So you can imagine, even if a robot did sense the force and fed it back to the console, that would generate a motion at the console, but then the robot thinks that motion is a motion that it should execute. So then it starts applying a force onto the tissue. That higher force gets fed back into the console. And so you have this cycle that could potentially create an instability. This is a well-known problem in the world of kind of bilateral teleoperation, and there are ways to address it, of course, and people work on it. And yeah, it's just, I just want to highlight that there are some of these challenges, and it'll be really interesting to see what kind of performance we get as we see force feedback start coming into surgical robots in the coming years. And then as I kind of start wrapping up, I wanted to talk a little bit about deep learning AI for medical imaging. So this would be a combination of sensing and compute. How this would work is you have just a lot of diverse labeled images. You collect as much data as you can, ask experts to label those images. That gets fed into a neural network that gets trained to then make predictions on where the anatomy is in those images. Now, you know, this is something that you can use for diagnostics, of course, but I think an exciting future direction is how AI can be combined with robotics for intraoperative situational awareness. So a robot needs to have an understanding of its own state, some of the modeling questions I was talking about before, but it also needs to have an awareness of where it is in the body, how a clinician is commanding the robot, where the anatomy is, so that we can work collaboratively with the clinician. And what I'm personally excited about is how robots can provide this minimally invasive access and then have robotically captured images. So I've got an example here of a robot arm with an ultrasound probe, but this could also be an intracardiac echo, providing these endovascular images. And then that robot can then do the segment with those AI algorithms, can do the segmentation on the images And because the robot has a sense of where it is in the body, we can then do 3D reconstruction too. And so robotics working together with AI, I think it's an enabling technology for allowing AI to be used intraoperatively, right? So we can imagine, yeah, as clinicians are performing their procedure on the heart, we can have 3D reconstructions of the heart, and the robot can have an understanding of where it is relative to the heart. That's a future direction I'm excited about. Of course, as engineers, we'll keep working on these challenges. And as I wrap up, just wanted to make a comment on the importance of engineer and clinician collaboration. Love hearing feedback from clinicians on these devices. Of course, we're always working on the technical side, and so I always want to hear your guys' thoughts on what capabilities you'd like to have, what your frustrations are with robots, and continue pushing forward on this technology so we can provide good patient care. That's it for me.
Okay. Well, thank you so much, Andrew. This was very informative for us. I think very important for us to learn more and more about how a robot functions basically. If it is okay, we would leave the questions for the discussion, which we will have after the technology-oriented talks. And I would like to ask Pablo Garcia from Laser Medical to tell us a little bit about the development over the 25 years that surgical robots have been around. Pablo, please.
Thank you very much. Just put this on slideshow. Great. Can you see my screen well?
Yes.
Okay, great. So maybe just a little bit of background about myself so you know where I'm coming from. I worked for many years at the Stanford Research Institute. I'm a mechanical engineer by training. In 2015, we started Verb Surgical, which was a joint venture with between Google and J&J. So spent 4 years designing the system. And then transferred more into, when we got acquired by J&J, transferred more into digital surgery, which was developing software applications for the lab. And then now I'm leading a company that is doing an imaging system for the cath lab to augment ultrasound imaging using robotics and AI. So what I'm going to talk to you about is based on my experience designing a robot from scratch and how things have evolved since Intuitive's inception, which Intuitive started in 1996. I joined SRI in the same lab where Intuitive span out of. So Gary Gotthard was a controls engineer in that lab. And so it's been really interesting to follow the trajectory of both of the technology, the business, and etc. One thing, when we started Verb, we really, a robot it's got all the hardware, which is addressing the hand-eye coordination. But the aspect that we also wanted to address was perception and decision-making. I'm going to focus a bit more on the hardware side. But I'll talk in the end a little bit about perception and decision-making and how that can augment the hardware. So when preparing this talk, it was hard for me to decide how far to start. But I decided to start at some fundamentals that, have not really changed in the last 30 years, no matter what you do, no matter how you start designing a robot. There are some fundamentals that are driving the design, and I think it's important to understand those. So, so the first thing is fundamentally you're trying to move a tool in space around the fulcrum, and so we have our workspace, and we're moving the angles of the tools in order to cover that workspace appropriately, and we're doing it by we're delivering. The function of the tool is to deliver forces on the tissue and to counteract the torques on the fulcrum. And the combination of that motion on those forces is basically what the robot does. That is the reason for the robot to exist, to deliver that motion, deliver those forces, and everything else in the design of the robot is driven by those parameters. So the workspace is really so, and that's basically driven by the statics and the dynamics of the tool moving in space. The workspace is the other key parameter that drives almost everything in the design of the robot. When you're doing surgery in one quadrant, where you're doing 2 quadrants and 4 quadrants, it becomes an increasingly complex problem as your tools have to move through wider angles. And when we started back in 1996, it was 3 arms. Now it's 4 arms. People have tried 5 arms. It's settled on 4 arms, but 4 arms on multi-quadrant is the reason that the XI exists, basically. And you can imagine that as the tools are moving through space, then the engineering headache becomes, how do you move all those tools without colliding with each other, colliding with the patient, with arms with each other, etc. Those are really driving the whole design. So so I would say that the 2 things that drive the whole iterations of the design is one is the motion fidelity, and the other one is the collisions over the workspace. And the motion fidelity is your ability to translate, as Andrew was describing, the input into as accurate of an output. So if I'm describing, if I'm following a circle on the input side, I'd like that to be a circle on the output. But if you have a flexible system, you can imagine if you have a pencil that has a spring in between you and the tip of the pencil, if you try to draw a circle, you're not going to end up with a circle. You're going to end up with something else. If you have latency in the system, again, it's going to be hard to follow that trajectory. And so all the design parameters in the robot are basically geared towards ensuring that you have that as high fidelity as possible. And then the collisions of work over the workspace, I'm not going to draw what happens with the blue arms that are holding the tools, but you can imagine as you move 360 degrees through this whole space, it becomes a real mess. And this is the reason why the XI is coming from the top, allowing basically a pivot almost around the center of the workspace, so you can get all those 360 degrees. And when you look at the evolution from the first robots that we designed on the Da Vinci S to the SI and so on, the whole morphology of the robot was really, the evolution of that morphology was being driven by this problem. How do you avoid the arms colliding with itself to cover as many quadrants as possible in a way that is easy to set up? The other concept that is critical is bandwidth. There's the human hand. When you conduct a task, you're able to, when you move slowly, well, it's pretty easy, right? As you start moving a little faster and faster, at some point, you're not able to deliver the speed that you need in order to follow a motion, and that's basically the limit of the bandwidth of your system. So a human is able to deliver up to maybe like 7 or 8 hertz, meaning that I could move back and forth at 7 to 8 times a second, but beyond that I can't really move. So when you're doing a complex task, I have to be able to have a system that is able to at least deliver that frequency. And what happens is in robots, every one of the joints is a spring. And at the end of the spring, you have a mass. And effectively, a spring and a mass have an inherent limitation in bandwidth, in flexibility. So if I have a very large mass and a very flexible spring, my resonant frequency is going to be very low, and I'm not going to be able to follow those motions at a frequency more than 1 hertz or 2 hertz. And I really want to get to 4, 5, or 6 hertz in order to actually deliver a motion. So this simple thing is what drives a lot of the size, the length of the joints and everything. I just want to have it in there because I'm going to talk a little bit about how some of the current design meet or are not meet those types of requirements. So reach, access, and collisions. This is what drives many of the designs. If you think of the tool moving over its angle, if I want low collisions, well, it's great. You can hold it here at the top. This is actually what you do with laparoscopic surgeries, right? You have the tool being held at the top and you're just moving it over the angle. The problem with this is that now you need to have a robot that is able to deliver a very large motion over the angle in which you're moving the tool. And so a robot that is designed with that morphology, for example, is the Cambridge robot. A lot of the serial robots that have been tried have that type of morphology. The problem with that is that if you wanted to cover multi-quadrants, you'd have to have an enormous robot, and that doesn't become practical. So typically these robots are good at single quadrant, double quadrant, but not at multi-quadrant. You have to almost like move the whole platform around the table in order to reach the other quadrants. Instead of holding the tool at the top, you hold it somewhere in the middle. Well, then you have some collisions, but you still have a reasonable robot for a large workspace. So this is how the Da Vinci is designed. You have, instead of a serial mechanism, you have what we call a 4-bar linkage mechanism, and basically what you're doing is holding the tool somewhere in here. There's about 200 millimeters from the fulcrum or the remote center of rotation to the first joint, and this is basically what dictates the amount of distance that the robot needs to move in order to cover the angles that you're looking for. So this is about 300 millimeters. You're still now left with about 600 millimeters of distance from the place where you have to hold the robot, and this is what determines the size of the robot. And this type of parameter is really what drives the size of the arm. And so what happens is, as you go larger in this space, you go back, this length gets bigger. And as your length gets bigger, it gets more floppy. And as you get more floppy, you have to make it bigger. So it's kind of a vicious circle in terms of design. And you have to reach a compromise in which you have the right range of motion, the right stiffness, and the right size for the robot. So what happens is, when we started designing the Verb system, we started pretty small, right? So it's like, great, we're going to make a tiny robot. Well, okay, so now you can't reach all the places. So you start increasing the size, and you still want to get to this magic number of bandwidth between 4 and 7 hertz. The problem is that the frequency goes down inversely with the length. And so as you start trying to reach a larger workspace, your arm gets bigger, but it gets thicker and it gets heavier, and so you end up with a pretty big system. And it's really driven by the workspace and the stiffness. So the robot has the 4 key components: the base, the setup joints, the active joints, the tool drive, and the tools. The 2 basic types of robots are either setup joints with spherical robots in the active joints, or you have serial mechanisms like the Cambridge, robot, where you have all the active joints from the base. All the joints are moving, basically. There's been many embodiments. If I take a look at the first robots were the Da Vinci S. The Da Vinci S was 3 arms. It was all the drives for the actuators, both on these active joints as well as the tool drive. They were all basically on the base. It was a mess of cables going all the way to the back. The reason they used cables with motors was to ensure that the system was sensitive to forces and was back drivable. That eventually evolved, and they tightened up on the setup joints. They made a telescopic drive and reduced the number of cables, but still the tool was still driven by the cables, but it was fairly wide. And the XI, the big changes there was coming from the top to ensure those 360 degrees of workspace, slimming the tools so that you could put them, the trocars, a lot closer, and then eliminating all the cable drives except for the tool, which makes the system a lot more robust and stiff and so on. A little bit less back drivable, but still a good compromise. And then you have the single port ones, which is a completely different architecture, and I can talk about, but I'm just going to skip it. So when you analyze the different designs, I'll go through some of the existing designs. The figures of merit that we look at is typically fidelity of motion. This has to do with your ability to follow the trajectories, friction, controllability, etc. Workspace, which is your ability to reach quadrants, reach an axis for all the tools, collisions. You have advanced tools, and we'll talk to what degree. How easy is the workflow to set up the vision system and digital capabilities. And you can see, you can debate the numbers one way or another, but you can see that really where we've evolved, the fidelity of motion has been pretty good, from the beginning. Where we've really evolved this in workspace, reach and axis, reducing collisions, placing more advanced tools and capabilities, and making the workflow more streamlined, and the vision, improving the vision. Digital capabilities, we're still at the inception, starting to gain more traction, but this is an area where I'm expecting that a lot of these systems will evolve. So I presented the ones from Da Vinci because it's easy to see how it evolved and why and so on, but there's many flavors. There's a lot of, from the beginning, computer motion tried a table-mounted solution. The problem is that the performance, if I go back to the fidelity of motion, it was really poor, and it had only 5 degrees of freedom instead of 6, so it didn't really succeed. This was the original system that Medtronic actually got from DLR in Germany when they started the robotics program. It was a beautiful system with a serial robot, but the problem is that it was really it was not really something that you could engineer into a product. So they ended up getting this other system that's a lot uglier, but it does withstand the number of cycles that you would need. And then you have Mantra. I think there's going to be later a talk over it, which is cart mounted, pretty much the same architecture as Hugo, the same architecture as the Da Vinci, but with individual carts. Cambridge, which is a serial robot that has the limitation that I was alluding to. This system that it was bought by Transenterics from an Italian company. It's not a great system. There's many problems with it, but it's out there commercially. This system here was the system that Oris developed, which included laparoscopic combined with endoscopic, so it had 6 arms. It's not being commercialized right now, but it's in the pipeline from Ethicon. And this is just from one of the patent drawings. I'm not disclosing anything confidential, but it's the verb system that we had designed, and this is probably what they'll test later in the year. And the philosophy there is really, it's very similar to the Da Vinci. Instead of coming from the top, you're coming from the table. But the architecture has a spherical arm at the end and a set of setup joints that are active. Some fundamentals of actuators that are important, when understanding how they've evolved. Actuators have deliver force and displacement. Certain actuators like the electric motors, they're very good at magnetic forces, displace a lot of displacement, very low forces. And piezo actuators, which is what works with the harmonica instruments, for example, they do the opposite, very large forces and very little displacements. Natural muscle, whether it's an ant or an elephant, is a good compromise in between. So when we use electric motor for displacement, we need to put a transmission, and this is what Andrew was describing. The typical transmission is the harmonic drive. But this is what makes a lot of those robots heavy and elastic and so on. The addition of this transmission. And so things have evolved, but not a whole lot, because the harmonic drives were invented like in 1980 or 1970 by a shoemaker, actually, interestingly, in the US, and they're still being used in every robot today. We used a lot of cable drives initially, but cables are very hard to manage, and that's why eventually they were replaced by these transmissions. Things have evolved to I have not seen yet. We'll see if the ethical system is succeeding in terms of being a non-cart table mounted system. So things have evolved towards cart mounted. Spherical robots have been more successful than serial robots for a number of reasons. And the stages basically have tended to slim over on the distal stage. The size of the tools have settled around 8 millimeters because it's a good compromise to get the performance that you need and the radius of curvature and so on, versus making them much smaller. The thing that has not evolved a whole lot is the tools. Actually, monopolar, bipolar, harmonic, and staplers have been the same for many years. And this is really what could potentially change the landscape of how you design a robot, because ultimately, the whole robot is designed towards moving and actuating these tools. If you compare a human arm to, it's interesting to a mechanical arm. It's hard to do a one-to-one comparison, but the payload is much higher than a human arm. The bandwidth is higher. The resolution is lower. You have a lot more muscles, the weight is lower, and the sensing capabilities are different order of magnitude than what a robot does. So again, it's hard an apples to apples, but I would say that fundamentally the way that natural actuators are designed is very different and a much higher performance than the robotics version. The tools. The tools are really driven by the fundamental limitation of the material to be able to withstand the load at the radius of curvature that you're trying to deliver. So that's why current tools, they need attention in the cables of about 20 to 30 pounds, and this isn't the limit of fatigue. That's why they have a limited lifetime. If you make it much smaller, then you're really compromising the amount of force that you can deliver. And the nice thing about these tools is that I have a very small radius of curvature versus other architectures that are more flexible. Vision is really another area that has evolved from the beginning. We've gone from stereo to NIR to hyperspectral, and then we'll have AI enhanced images. I'm just running a little bit faster here because I'm running out of time. But what technologies could really change the game? So my perspective is things have evolved, but not really, dramatically. If you had tools that require different forces for cutting, require different forces and operated differently for suturing or putting tissue together, or staplers that were more intelligent, then you could really change that design of the robot. Because as long as you have the same forces and the same workspace, you're going to end up with fundamentally the same type of solutions. There's not a whole lot that you can do. Superhuman vision, which we've seen with multispectral vision, that's another area where it can dramatically change the experience of the robot. Actuators with twice density power weight, and I'm talking about the combination of the motor plus the transmission plus the torque sensor, etc., would also change the game. Cables that were 10 times stronger could really change the game than intelligent control systems. This is interesting. This was one of my favorite projects at Google, where put all these robots together. Each of these robots was basically learning through reinforcement learning to grasp objects. And there were like 100 of these robots connected. You can imagine if you have, 1,000 surgical robots connected doing 1,000 tasks, every time you're learning something, the whole system is learning and you're kind of evolving as you learn. This is the type of thing that can really change dramatically the way that you're acquiring knowledge and expertise. And this is actually an example of an autonomous robot that was designed at, the control system for a Da Vinci, one of the Da Vinci kits for doing fundamentals of laparoscopy that was doing it autonomously, based on AI deep learning techniques. And it's not at human performance, but hey, it's starting to get somewhere close. Do I have 2 more minutes? I know I'm at time.
It's fine. Yeah, sure.
Okay. So let's switch a little bit because surgery is really about making the besides manipulating the tissue and so on, is really about making the right decisions. And so where a lot of the digital surgery aspect that I was alluding at the beginning can make the changes is in really starting to describe the procedure, finding patterns, modeling the relationships, and that will allow you to start predicting what is going to happen before it happens. And ultimately, if you have a robot that knows what's going to happen and is able to control it, then why not let it do it certain things? So that's the natural evolution. Obviously, there's many hurdles together, not just technical, but that's the evolution. And the other thing is the need for really optimizing the whole trajectory. So this is where a lot of the new technologies can really help. It's not only what you're doing, but how you planned it and how you're going to follow up, and really taking the burden off each of the players in the treatment, so that they can coordinate information better and ultimately benefit the patient from not having gaps. And I'll just close saying that typically this is actually a futurologist that was at SRI in the 70s, and he used to say, which is I think still applies, that we tend to overestimate the impact of new technologies in the short term, but we underestimate them in the long run. And this has happened anywhere from computers to cell phones. And when it comes to AI and digital surgery, I feel it's a little bit the same way. Probably not much will change over the next 5 years, although there might be a lot of hype on it. But over the long run, it's completely going to change, the way that things get done, both in the operating room as well as outside the operating room. Thank you very much.
And thank you for explaining this technology and also the engineering. Now we are going into the clinical practice, and we have a person that knows very well how to use the robot to operate on humans, and especially the mitral. So I would like to introduce Sloan Guy from Georgia Heart Institute in the US. And he will tell about what can surgeons expect from the robot device in evolution.
Thank you so much, and thank you for having me here today to talk about something that I'm very passionate about, which is new robotic system development and how that might be useful for cardiac surgery in the near term and the long term. So what we're going to talk about here is the new systems. And as a big disclaimer, I would say that we've tried to include all the systems, but I say that rarely a month or two goes by where I don't hear about some robotic surgical system in the world being developed that I've never even heard of. And I'm a zealot who is very tapped into what's going on. And even I am surprised that new robots are being developed we don't even know about. So we've tried to highlight those that we do know something about and that may be useful for cardiac surgery. Let's see here. These are my disclosures. So I'm going to give you a few eye-opening facts of some importance. The first thing to know is that only Intuitive Surgical has FDA approval in the United States for cardiac surgery. No other robotic system does. The Intuitive Da Vinci 5 system, which we're going to go over, which just came out, was approved for all specialties that the XI is approved for, except for cardiac and pediatrics. Although Intuitive has formed a development group, if you will, to sort of make decisions about how to potentially roll it out for cardiac surgery, perhaps in a better way that's been done before, but not clear what's going to happen there. The FDA is requiring approval for each procedure for all new systems. And by report from our friends at Intuitive, they are requiring human studies being done under an IDE, small series feasibility studies, which include both experienced and non-experienced operators for each procedure in each specialty. SS Innovations, which is led by Sudhir Srivastava, our cardiac surgical colleague, is the only company in the world that I've seen that has made a 100% commitment to cardiac surgery. We're going to do it no matter what. Not sure exactly what percent that would be for Intuitive. It's quite high, but other than Intuitive and SS Innovations, we do not have a firm commitment from any company. Many of the other companies have said that they may pursue cardiac at later stages after the initial phase. The European Union is classifying recently any devices that touches the heart as a class 3 device under the MDR, which requires human studies and reapplication. So recently, Intuitive Surgical announced that they would be not supporting cardiac surgery in Europe, and that's despite the fact that robotic heart surgery in Europe and the United States is growing. So here's the robotic surgery universe in 2024. And again, there's many companies missing here, and these are primarily devices that I think might be useful for cardiac surgery, whether they're being used for it currently or not. So there's the virtual incision robotic system, which is a single port system. That's the one that was used in space this year. Vicarious surgical, Medtronic, Intuitive, of course, J&J, and Ascensus, which took over Transenterix. In the UK, we've got Cambridge Medical Robotics, or CMR. In Germany, we've got Avatera. In India, we've got Sudhir's group with SS Innovations. In China, we've got Renovo and also Tianjin University developing surgical robotic systems. The Korean company, Mir Company, and Medicoroid in Japan. This is the robotic surgery galaxy, if you will, and this is a borrowed slide, but basically to think that that robotics in medicine is only growing and surgery is only growing in select specialties is wrong. There's an explosion of robotic systems being developed for lots of specialties and lots of applications outside of surgery. So this is the Da Vinci 5 system, which was unveiled recently and FDA approved, and it's got a number of improvements over the Da Vinci Xi. First of all, it's a smaller platform, so both the surgeon cart and the bedside cart are smaller. There's force feedback of some of the instruments. The haptic controllers are redesigned a bit. You're able to manipulate the computer system while your eyes are in the surgeon console much more easily. So it's really a very modernized culmination of all the lessons that Intuitive Surgical has learned over the last 30 or 35 years. I really do like the surgeon console ergonomics. You can basically put it wherever you want your head to be, and it's just a much smaller presence in the operating room, and we all know that that's useful. There's a number of other features like CO2 insufflation is incorporated, et cetera, but there's no doubt that that's a big step up in technology, although not really a paradigm shift. If you can do an operation on the heart with the XI today, you could probably do one with the Da Vinci 5 tomorrow with a little encouragement from the company. This is the transenteric system. The Achilles heel of this system is the instruments were not initially wristed, and wristed instruments are really the major contribution of robotics. Without wristed instruments, I don't see a lot of advantages. And this was basically designed to capture laparoscopic surgeons who wanted to do robotics, but kind of wanted to continue doing things the way they always did them. So I'm not sure that's ever going to be useful for cardiac. Cambridge Medical Robotics is a great robotic system, and it was the first one that I'm aware of publicly that showed an open cockpit model for the surgeon console with the 3D glasses, along with each arm having its own individual bedside cart, which at first I was skeptical of, but now I realize for cardiac brings a lot of possibilities of putting arms on either side of the table, perhaps redesigning the operation a bit. For either coronary or intracardiac, and possibly even having 5 arms, which opens up the possibility in my mind of having a true robotic assistant that would be at a second surgical console actually assisting us. This is the Hugo robotic assisted surgery system. It is also modular. It's an open cockpit model, just like many of the new systems are. And they're putting a heavy emphasis on digital surgery. Of course, what's really happening in the market in the U.S. is that you've got the old U.S. Surgical, which became Covidien and is now Medtronic, which was, U.S. Surgical was a laparoscopic company, and J&J, you've got Ethicon, which was also a laparoscopic company, and those two companies resisted robotics for many years. And finally, they just had to realize that it's going to happen no matter what, and they've got to either develop it or get out competed by the robotic companies. So that's what's happening, and so both have developed very nice robots. I think that Medtronic is one of the more promising ones for cardiac, only because Medtronic, as you know, was largely started by cardiovascular folks. So it's got deep roots in cardiovascular. Titan Medical was one of the early pioneering companies to develop a new robotic system, but it ran into a lot of financing problems, and unfortunately, it basically has become a shell company where it's licensed out its technology to, I believe, Intuitive and maybe Medtronic, and so it's not really a viable entity at the moment. But the technology that they developed is not lost. Vicarious Surgical makes this really cool robot many of you have seen, where it goes to a single port and it sort of opens up like an insect with 2 eyes and 2 arms. I think that's pretty cool. I could imagine that being used in cardiac potentially at some point. The mantra in India, I think, is one to really pay attention to as a cardiac surgeon. Now, Sudhir, and as a disclaimer, Sudhir was a partner of mine here in Georgia many years ago, and I just am so impressed with what he and his company have done and the perseverance. His goal was to build a cheaper robot, much cheaper than Intuitive, to make it therefore available to a much broader population throughout the world, and then made a very solid commitment to robotic cardiac surgery. So I think that we will see this robot eventually in Europe and US, and it will be important for cardiac surgery because of its very clear commitment to our specialty. The Medicoroid robot looks very similar to Intuitive, but it's got some improvements with a smaller bedside cart and a very nice surgeon console, and I think that's going to go a long way. Robotics is exploding in Japan because, to my knowledge, Japan is the only country that actually reimburses robotic procedures at a higher rate than non-robotic procedures. Whereas here in the US and other places, you basically get paid regardless of how you do it. So there's some incentive there. There's the Carina system from Renovo Surgical in China. Again, modular with different, each arm having a different base there. There's the mirror company, the Revo in Korea, which is very similar to Intuitive. This is the Shenzhen University micro hand robotic system. This is the German system. A lot of the robotic technology has come out of Germany, and I really like these smaller surgeon console, headpieces. There's a lot of debate in the field about whether an open cockpit with 3D glasses is better than a more immersive experience. The fundamental of that debate is that those that espouse an open cockpit with a screen and 3D glasses say you'll be able to communicate better with the team. Those that prefer the more embedded experience, where you've immersive experience, where the surgeon's head is in the actual console, favor that you can operate more efficiently within the robotic environment. My prediction is many of the systems ultimately will have both options available for surgeons, depending upon what they prefer. These are some of the various surgery consoles, and as you can see, some of them are open cockpit, some of them are immersive. And but all of them have one thing in common. All the companies are working towards improved ergonomics for the surgeon. All the companies are working towards enabling the surgeon to be able to control more functions while engaged in the robotics space through computer engineering. And we're just going to see more and more improvements as time goes on. The master controllers, this is one of the most fascinating things that have happened in the development process. And Pablo, the last speaker, and I worked on the Verb project together. And I remember, having a vigorous debate about, what it should look like. Should it be a little ball in your hand? Should it look like a video game, like an Xbox controller? Like you see, look at CMRs, it looks like an Xbox controller, sort of. You've got the intuitive system, which is tried and true, and we've all used that for years. And then there's different types of controllers. So lots of innovation going along the masters space. Again, my prediction is 10 years from now, each robot will have different master controllers, depending upon what the surgeon prefers. But we'll see. The arms are largely unchanged. I think Pablo touched on this. Basically, they've got 6 or 7 degrees of freedom with straight shafted instruments that then articulate at the end. Other than transenterics, although they have worked on it in the past, having articulated or instruments that have degrees of freedom at the tip, which I think is essential. But no real snaky arm options yet. But we would like to see that eventually in these robotic systems, so that port placement is not as critical. This is the transenteric system, and you see the surgeon working there with the master controllers, just to give you an idea of the gimbals that you use, and it's really interesting. I love this robot here. It's just fascinating. The single port robot, and I'm pretty sure we could do a robotic mitral with this, other than the fact that it lacks a stabilizer, but certainly we could sew a coronary with this robotic system. So we'll see. This is Sadir's robotic system, the Mantra. I will say, I think they're on their 3rd generation of developments. So each iteration of it gets progressively more advanced. I've had my hands on the most recent system, and I will tell you that it's very usable. I could do a robotic case with this in cardiac today, and I had the privilege of watching a couple of live robotic cases in India recently. So it's a very usable system and very familiar to those of us who've done robotics for a long time. So it would not be difficult to incorporate this into our practices. And again, they've made a strong commitment to cardiac. The Metacoroid system you see here is just a fabulous system, and I think has a lot of promise. We would like to see this be available worldwide, and hopefully it will. I think we're going to see a lot of development outside the U.S., which ultimately will come into the U.S. From our perspective in the United States, will be a very good thing. We're seeing innovation really everywhere now. I think robotics in surgery is one of those things, a lot of people, in particular in cardiac, have tried to sort of stop it, but it is an unstoppable force. It is so useful to what we do, and many of those older surgeons who resisted it at the local and national levels are fading in their influence, and there's just no way to stop this revolution. It's happening, and it's going to continue, particularly with so many companies involved. We talked about the transenteric system. It is FDA approved, CE mark approved, does have some haptic capability. But again, the big problem is it does not have articulated instruments that have the degrees of freedom at the tip, which is a major problem as far as I'm concerned. Cambridge Medical Robotics has really done a great job putting together their robotic system, and as has the Medtronic folks, and they've made a big emphasis on digital surgery and recording and analyzing cases, et cetera. They want to expand minimally invasive surgery. They're very committed to modularity and innovation. I think a lot of the companies are focused on making the systems appealing to those of us who don't currently do robotics, or say abdominal surgeons that do laparoscopy. And, there is some value in that. Or with a modular robotic system, perhaps you don't do the whole thing robotically, but, you have a couple of instruments, a camera and a retractor perhaps, or something like that. So I think there's going to be a lot of exciting things that are going on in the next, 10 or 20 years. Here's a picture of Sadir, who really has just been an unbelievably unstoppable pioneer in this space. And I think he's the one leader in the field that I've heard has really pushed the idea of making robotics cheaper. And I don't doubt that any administrator in our country, in the United States, would disagree that that should be a high priority. And I think it will get cheaper. I mean, we all know from cell phones and computers that as technology gets more competitive, the price goes down. But he's the pioneer that's really pushing that. And he's looking at building all current cardiac surgical instruments, but also perhaps some new ones. And they've done over 1,000 clinical cases in all specialties, including a good handful of cardiac procedures. So I think that's very promising. I think we're having a talk on that coming up, one or two talks. The Metacoroid robot has also gotten some regulatory approvals and is just a fabulous robotic system. This is the sort of marketing for vicarious surgical, and this idea of a single port incision, I think is a good one, although somewhat limiting for those of us who need a retractor. The German robotic system, again, never discount the Germans. A lot of the robotic engineering has come out of Germany. They've tried to work on communication, improved communication system, improved tools. This is the project that Pablo Garcia and I worked on, which is the Verb project. And you see the same picture there that Pablo shared. But basically, the idea was that it would be table mounted, and there would be, again, a heavy emphasis on digital surgery, and really built an incredibly nice robotic system. Well, then J&J acquired Aris Robotics, which was founded by Fred Mall, who also founded Intuitive Surgical, also founded Hansen Medical. And Dr. Mall had developed with his company another robotic system called the Atavia. And so the company essentially sort of merged Verb into Atavia. And that is the robotic system, I believe, that they're moving forward with, although a little bit unclear. It's sometimes hard to get that information. The J&J robot has multiple arms. The Atavia system, much like the Verb system, is incorporated into the bed. So the bed and the robot are one device, which has advantages and disadvantages. A lot of the systems have these systems like Medtronics to incorporate video analysis, performance analysis, et cetera. So here are some words to wrap up to incorporate into your vocabulary: digital surgery, procedure segmentation and analysis of performance, and machine learning algorithms. Okay, a few important concepts. Okay, most companies will start clinical projects in non-cardiac procedures because it's low-hanging fruit and higher volume, and frankly, many of the procedures are far simpler. We need significant input of cardiac surgeons. If a company contacts you and says, "We want your opinion about the future of robotic heart surgery," meet with them and tell them about your passion, because we need this technology. People have forgotten the finances of robotic cardiac surgery. The companies, the highest robotic DRGs in the United States are robotic cardiac procedures, but the volumes are smaller, but the reimbursement is so much higher. So it takes about 10 prostates in my hospital to bring in the same amount of money as one robotic mitral valve surgery. So that excites the hospital, but not the robotic company, because they get to paid the same. Lots of new tech developments, flat screens, open consoles, new master controllers, new instruments, digital surgery, quality improvement with automated analysis of performance, modular arms, more arms, robotic arms built into beds, cost reductions, new financing models, haptic feedback or force feedback, autonomous systems, or at least assisted functions, I think or a human enhancing human performance is coming. Global competition, I think, is huge. We've had one dominant company. They're not going to be as innovative as if there's a bunch of companies competing with them. And I think that even Intuitive will be a better company as a result of this competition. And there's the possibility of having a true robotic assistant. And so final conclusions. Number one, there's a tsunami of robotic systems coming worldwide. It's a tsunami. I mean, I've probably mentioned a third of those that are out there, okay? The FDA and EU have inadvertently put cardiac at a disadvantage due to insisting on, in the FDA's case, per procedure approval, and in the EU's case, additional approvals for cardiac. I don't think this was on purpose. But it has had a disproportionate impact on us, which we need to work on with them. Intuitive Surgical remains committed to robotic cardiac surgery in the US, but not currently in the EU, although I'd like to see that change. Their commitment moving forward, it's something that I think we can influence if we continue to meet with them and encourage them that robotic heart surgery is in fact growing, which it is. Both in the US and Europe, and robotic cardiac surgery will prevail. The first time I watched my mentor, Doug Murphy, do a robotic mitral, I realized there was no way I would want to have my operation done any other way. And I think that it will ultimately be standard of care for many of the procedures that are doable with the robotic system. Thank you very much.
All right, Sloan, this was a fantastic overview. Thank you so much for that. And we will now start a 10-minute discussion. I would first ask our audience to put questions into the Q&A function of this Zoom system here. And I would then like to ask our panelists to start out with questions to our engineers. Sam, you are muted.
Yes, thank you. Thank you, Johannes. What a great first hour of this webinar. 3 excellent talks. And Sloan, that was an unbelievable survey of everything that's out there. I had a question for Dr. Garcia. In your talk, you talked about the different iterations of the intuitive robotic system from from the original to the S to the SI to the XI. And I saw that fidelity kind of went down with the XI compared to the SI. Is there a reason for that? I'm one of the few people that continues to use the SI for instrumentation reasons. And I was interested to see that was the case in terms of the fidelity.
Yeah, okay, so there's always compromises that you need to make. And in this case, the fidelity goes down because the transmissions are driven by not cables, but by little motors, and you have some more friction and losses. And also the latencies are a little bit higher. And so for most people, that doesn't make a difference. But if you really wanted to push you can measure the difference. And if you're really pushing the envelope in terms of the speed at which you move, you would notice it. It's just reached a compromise where, for the most part, it works well. It just allows you to simplify some of the design of the system in other aspects. So everything is about trade-offs, and so there's that's what this is. It's a trade-off where you've made a little bit of a compromise on performance to make the system smaller, more compact, and simpler.
Great, thank you.
Bob, please.
Thank you very much. This was an unbelievable first hour. I agree, as Dr. Balke mentioned. But my question from our engineering colleagues, Dr. Urakov and Dr. Garcia, was one of the disadvantages that cardiac surgery had was the congruent technology was lagging, as was mentioned. Why would you say that there wasn't any, you can say, movement in the past in trying to allow the congruent technology to be available so that cardiac surgery could continue to progress. And I think the reason why Intuitive put cardiac surgery in the back burner, because they weren't interested in, you can say, putting all the research and development in the congruent technology that's required for cardiac surgery. Maybe, I don't know whether you have the answer to that or not.
I'm sorry, congruent technology that.
Yeah, that you said there was a lag in the technologies that existed, like the cutting, all the other, you can say aspects of it in terms of the instrumentation that required to make cardiac surgery. Like they put all the emphasis in cardiac surgery initially, and then once it became apparent that cardiac surgery needed more instrumentation, the stabilization, the suturing, all those kind of technology that requires for cardiac surgery to be able to be further advanced, they kind of stopped. Like, is it difficult to try to come up with those technologies specifically for cardiac surgery? Is that why there has been a bit of, you can say, halt to further progression?
Okay, so there are two different things. So with existing surgical tool technologies, I think it's more of a business decision and regulatory decision, because the regulatory hurdle is higher and the return on investment is lower in terms of volumes. That's the main reason that a business like Intuitive will choose other applications over cardiac. It's no question that, you know, you do require a wider set of instrumentation and tools to enable cardiac surgery, but overall that wouldn't be a problem if they consider that the return on investment, you know, was worth it. What I was alluding to with the tools is, you know, the fundamental a tool that touches the tissue, and what it does is that in the tissue has not changed much over the last 20 or 25 years, you know, whether you talk about monopolar, bipolar, staplers, etc. And, you know, I do believe that there is opportunities to change that. And if you did change that, then that would allow basically smaller instruments that could snake into places that you can't do right now. You could probably do things intracardiac instead of, you know, coming through minimal invasive. You could do a number of things that you couldn't do right now. But that's a different space. You know, you'd have to fundamentally change the way you cut and change the way that you put tissue together.
Thank you.
Yeah, nothing to add for me. I think I'm not sure it's a technology problem or the business case and regulatory issues. How all those pieces come together.
Thank you.
And now we have a question from the audience. Dr. Sudhir Srivastava asked how important and realistic is focus on haptic, considering over 12 million procedures have been done without it, and can it really help the accuracy that human touch receptors have?
I'd like to answer that if possible. So I think that Sudhir is right, that we can easily do cases without haptic feedback. And somebody actually studied this. There's a paper that shows that after about 20 cases, a novice surgeon begins to be able to do maneuvers without haptic feedback comfortably. Now, the downside is that haptics, it's an important sense as we go through our normal day in the world, right? And when you take a sense away from a human being, you know, their other senses are enhanced. So if you take away my eyesight, I'll have superhuman hearing. I mean, that's well known, well established. So I do think there's still a price for the elimination of haptics to be paid. I think even if you were to watch me, and I've done a lot of cases, open and robotic, and you watch me operate open versus robotic, there's no doubt that I'm still going much faster with my hands than I am robotic. And I think part of that reason is that your mind self-consciously, or maybe unconsciously rather, slows down when it lacks that extra sense of haptics. Now, the problem is haptics is much more complicated than force feedback. So the new, DaVinci 5 has some force feedback when you pull a suture or whatnot. If you remember back to medical school, there's Mesner's and Persinian corpuscles. There's pain and temperature. There's pressure. It turns out that touch is a much more exquisite entity than just force feedback. And I think we are a long way, even in the laboratory, from having anything that resembles the kind of touch that we feel with our own human hands. And it's a lot of work and a lot of expense that may not actually be as valuable as some of the other developments, as Sudhir alludes to.
I have a question for our two engineers, Pablo and Andrew. Is automated collision detection realistic? And what are the limits to that?
Start, Andrew.
Yeah. I'm not sure what the current commercial products are doing. But if you've got a calibrated kinematic model, the robot should be able to predict collision. I think the question is, what do you do about that? And how do you plan motions around collisions? That's a harder problem, but just saying a binary yes or no, the arms are collided or not, is something you should be able to implement on a robotic arm. I'm curious, the motivation for the question. Sounds like that's a problem you've had.
Yeah, currently we have to manually correct collisions. I mean, some functions were integrated now where if arms collide, you can press a button and they move apart. And my question was, could that be an automated process where one arm knows where the other is and they wouldn't collide automatically?
So just a couple comments on that. In theory, yes. The challenge is that these arms, you try to make them as small as possible. And because you try to make them as small as possible, that they have a little bit of elasticity, and this kinematic change, where they are in space, but there's a bit of error. So if I model the arm, the computer would be able to guess where it is in relation to the other, but it would be putting an error of maybe like 20 to 30 millimeters, let's say. Okay. And since they're in such close proximity, that's enough to basically not be accurate enough. You'd need something that is a lot more accurate.
Okay.
So that you could implement a different solution, which is more putting like almost like a skin that senses where the other arm is in relation to its position. But again, like a lot of these things, for the same reason that haptics, it's a bit more of a trade-off. You're putting a feature that is going to be complex and expensive and prone to failure. And if people can deal with those collisions manually, then it's at least from a product perspective, it's a fine solution. Technically, sure, you could definitely, and what you're saying is true. If you had enough accuracy, you just move those robots away from each other. So technically it's doable, but it's more, is it worth the bang for the buck in terms of the product?
Okay. Pam? You are muted.
I had a follow-up question, just kind of pursuing the line that Sloan was talking about. So when Sudhir brought up the topic of haptic feedback, I was going to, like in my own mind, I've developed visual haptics such that if I move tissue, I can tell if it's calcified, I can tell if it's small, if I want to figure out where I want to go on a coronary, I can make up for it. But when Sloan said the speed, I think that's important as well. And speed is absolutely compromised when all you have is visual haptics. You can figure out some things, but speed does not improve or can't be made to be equal to the open setting. And so my question to the engineers is, it seems to me that spatial awareness inside the thoracic cavity or inside the abdomen, if you're operating there, is one of the impediments to speed as well. As I'm training a junior partner, one of the things that I see that it's very difficult for the juniors to figure out where they are inside the chest, and moving around is very, very slow. Obviously, we encourage that because we don't want injuries to vital structures. But at the same time, is there some implementation in the technology that can perhaps enhance or shorten the learning curve for spatial awareness, digitally, for example?
Yeah, that's a really interesting question. So actually, it's a question that we looked at quite a bit when we were designing the system. There's definitely ways in which you can integrate a virtual environment to give you a bit more of a context and spatial awareness together with zoomed in interface. You know, human vision has very wide field of view. But there's always a compromise between how much you zoom in versus how much of the panoramic you cover. And
or what angle your
honestly,
camera is at. It's
sorry?
hard when you're in a 30 down versus a 30 up, for example. That's a well-known fact amongst all of us.
Yeah, so I think it would, so it's, the technologies are possible, and I think probably that is one of the areas definitely that there needs to be improvement. Why is it not done today? Well, I mean, the stereoscopic displays that you have, they just have a very limited angle of view. They have maybe like, you know, 40, 50 degrees, something like that. And you would need displays that have a much wider angle of view and are able to combine the zoomed in with the zoomed out. But I think it's a great area where there needs to be improvements. Again, technically, there are possible solutions.
Pablo, is there a way to digitize visual haptics such that the computer itself would give us sort of simulated haptics, if you will, by interpreting the interaction of the bot with the
Yes, and
body?
people, yes, absolutely, and people have done that, and to some degree, where you kind of look at the bending of the. I mean, this is what you're doing actually when you're looking at. If I looked in your brain after done hundreds or thousands of procedures, you're feeling the tissue. You know, the part of your brain that is activating is probably the same one that you use for your sensing. You're using how the tissue deforms, how the tool deforms, you know, to basically interpret. So it is possible. I haven't seen any work that I think if you applied AI techniques, you could probably extract a good signal out of it. It's a good area, probably. You know, you're still the challenge is that you're inherently limited because the latency between the vision and you is about 160 milliseconds or so. The feedback is not as great as if it's like haptic feedback. You know, you're going back to the bandwidth thing. The 160 milliseconds is already giving you a very poor feedback in terms of the bandwidth. But yeah, it's definitely an interesting area to try.
Okay, I thought this was a very inspiring discussion. Super. And now we go to listen to the early experiences of our cardiac surgery colleagues who have used the new systems. We start out with Satyaki Nambala from Apollo Hospital in Bengaluru, who has used the SSI Mantra system in cardiac surgery clinically. Please, Satyaki, tell us about how you felt behind the Mantra system.
Right. Thank you, Dr. Bonatti. And good morning, everyone. I hope I'm audible.
Yes.
All right, very nice. So just before I start, I must thank the Society for the Robotic Task Force, as well as the Society for putting this together. It's been absolutely mind-blowing listening to all the speakers before me. It's fantastic, very, very interesting, and very inspiring as well. So we've had the SSI Mantra system for approximately 5 months now, since the beginning of January this year. And to put things in perspective, we've had the XI for approximately 4.5 years now, since 2019 end. We have performed approximately 500 plus procedures with the XI system, and we've just done 11 procedures with the SSI mantra. The reason I'm saying this is whatever I say could, maybe a little biased because we have so much of experience with the other system and so little experience with this system. Now, having said that, like I said, we've done 2 ASD closures. We've done about 6 bilateral IMA harvests. We've attempted 3 TCABs with the IMA harvest, which is part of the procedure. So before I elaborate a little more, let me go back and show you what the SSI mantra is all about. Like it's been discussed before, this is an open console system or an open cockpit system. This is a 4K 3D resolution monitor that the surgeon looks at. Now, for me as a surgeon has been using the XI system to come back and start using the SI system the SSI system was actually not too difficult. We just had Dr. Sudhir Srivastava in the operating room. We had a few other of his colleagues, and very little brief instructions, and we could simply, with a little bit of training, or if somebody was already had some experience with the XI, this is not a very difficult system to engage with. The other apprehension that I had as a surgeon was, what would I do what would happen if I looked away from the console, from the monitor? Would the instruments move up by themselves? That was the other fear that I had, because the XI is a closed system and this is an open system. So interestingly, when you wear the goggles, the 3D goggles, and look at the monitor, the movement of the head is sensed, and which means that every time you look away, the instruments no longer move. So it's very safe to use. The issues that I had here was initially going back to XI after using this system feels a little claustrophobic now. So I think this is a very interesting system. The open system is possibly much more comfortable for most surgeons to use. Now, the other little problem that I had was that the pedals were too small for me if you're particularly using clogs, but these are very, very minor problems that I think are going to get rectified. Let me elaborate on the controls, the hand controls. Now, all of us as surgeons using the XI, we've used the pincer system. This has the finger grasper as well, but we have the palm gripper. The palm gripper is like holding a small mouse in your hand. It's got 2 buttons, one on the outside and one on the inside. The inside one is where, when you click that, it grasps or releases, and the outer button, which lies under the index finger, works like a clutch. For me as a surgeon, yeah.
Sorry to interrupt you. We cannot.
Yes, sir.
Your slides are not moving, I guess. Where are you now? On which slide number?
I am on slide number 4.
Yeah.
Am I not? My slides are not being seen?
They're not.
No.
They're not moving. We are at the first slide.
Oh, I see.
Yeah, just maybe presentation mode.
Right. Thank you.
You're welcome.
Why is it paused? I'm going to stop share and continue the share again.
Yes. Yes, fantastic. Yeah.
Is it seen? Yeah, very nice. All right.
Yeah.
So I don't think I need to go back. It's an open system. We've already discussed that. We're only going to look at the hand controls. For me as a surgeon, of course, with very little experience, the palm gripper seemed to be a little more difficult to use. But I think with experience, as I do more and more cases, this should become easy. And I did speak to Dr. Sudhir Srivastava last week. It can be replaced with a finger gripper, and he says something even more interesting is coming through. I don't want to reveal what it is, but he says something really, really interesting is going to happen. So this is how it looks. This is me operating on Thursday, doing a bilateral memory. I'm going to play this. And that's how you hold the palm gripper in your hand with the 2 buttons. It's extremely comfortable. The chairs are very, very ergonomically designed. It's very comfortable to sit at them. And I think with the lights off, with the 3D goggles on, if there's nothing to stimulate, one would actually fall asleep on those chairs. So it's very comfortable. The 3D vision is also extremely good. When you look at the video here, the monitor may not look very clear because it's a 3D monitor. And the movements are as comfortable as the the Da Vinci system. And as already mentioned, you have each of those arms sitting on their own cards. And again, like Dr. Guy said before me, was having a fifth arm can actually be very interesting in certain situations. So I'm not going to dwell more on these slides. I think for me, this is a very nice system. The beauty about this is, we attempted the 2 TCAPs as well. It is, but sewing still was probably. We were able to complete in as far as handling, the pronoma switcher is concerned. But otherwise, it's a fantastic system to use. This has been my experience so far. Now, a little bit about the camera system. It does provide extremely good vision. Of course, it's 3-dimensional. But what is interesting is that it has an articulated tip. And what I see with the articulated tip is that when I want to look up, the part that articulates sometimes strikes against the heart and then starts moving. And when I want to look down, especially if you want to take down the prima and you're looking at the proximal end, it's a little more difficult. Apart from that, it's a fantastic system. I don't want to dwell on this. We practically have all the tools that is required. I really have nothing else to ask for. The stabilizer, I was really impressed with. Stabilizer works really, really well. He's waiting for these. That's about it. Thank you very much.
Yeah. All right. Thank you so much, Satyaki, for giving us all these impressions. We right away ask Dr. Nitin Rajput, also from Bangalore, from Narayana Cardiac Sciences Hospital, to tell us about his experience with the mantra system.
Okay, good evening, everyone from here. Okay, am I audible?
Yes, we hear you well.
Okay, so here we are using SSI system for last approximately now 1 year. So I will share a few slides which are very much similar to Dr. Satyaki sir. This is an open console system, has 3 components: surgeon's console, patient card, and vision card. Open console system has a large 3D 4K monitor, along with a very useful 2D touch monitor. I will show the use of it. How can it be used with the maximum usefulness, and a good head tracking safety device. So these are the ergonomics. This chair is very nicely designed for the system. It comes along with the system. You can sit with your back straight up. So here you can see this is the head tracking device. If surgeon moves or look out of this monitor, this hands control stop working. The instrument will not move inside. Now you can see the secondary monitor here. Everything can come on this monitor. These are the controls with SSI. You can see a slave monitor here with all the vitals available to you. And you can see angiogram here without the need of any other monitor or computer system. Even CT scan and MRI can be brought here. hand control are different. Palmar grip, it very, very good actually, because your finger doesn't fatigue in the long run. If you do a long surgery, the palmar grip is very good. The hand clutch is there on one side and grasper movement on other side. It looks like this. Foot petals are pretty standard, no difference. Similarly designed like intuitive. You have camera and master clutch on the left side and cut and coagulation on the right side. So finally, the surgeon command center looks like this. Nice, comfortable. The best thing about this is you can communicate with your team in a better way, especially during intracardiac procedures in which you need an assistant on the patient side. You can communicate better way, and the noise which comes from the patient side, instruments noise, cart noise, and sometimes someone is moving something out and it comes in your ears in the intuitive system is not here. You can communicate in a better way. Patient carts, all arms are separately kept on the separate carts. It looks like this, and it has a digital display to work with, the battery backup, and this drive clutch. It drives with the battery system. So once you dock it and lock it, then it doesn't move. There is a good locking system which stabilizes each arm very nicely. So here is the button. If it is on move, then only this cart will move. Once the docking is done, you have to press this lock button. It will take few seconds. And once it turns green, it displays docked. And then it can't be moved. You cannot move with the drive enabling switch also. It gets absolutely stabilized here. So this is 7.2 feet height, very, very good. And the flexibility to use in the space along the patient table is very nice, so that the collision is lesser than the other system. And the provision of fifth arm is very nice. We haven't used the fifth arm, but we have used 4-arm system during MVR without any collision. Vision cart has a 3D monitor for OR staff also. The advantage is once the staff is inserting the instrument for the first time or during the exchange when guided tool mechanism is not there, he or she can see the monitor in 3D vision, so that the chances of getting injury inside due to lack of depth perception is not there. The camera is very nice. It's a 0-degree camera with the articulation system. So I will show a short video how it looks like when you articulate the camera. Now it is looking upward. It is similar to like 30-degree camera, and you can move it to the downward without touching the heart. If you place it very well, left, right, and right, left to right without any problem. So sometimes you just want to convert like 0-degree camera into the 30-degree, just articulate it, and sometimes it can move more than 30-degree and gives a nice vision. All the instruments are available, especially to mention cardiac stabilizer, which is commercially not available with the current other systems. So there are few differences. Everybody knows about the intuitive and SSI system. Here there are 3 points to mention. One is open console system. Other is flexibility of using the separate arms around the patient, and vision card having a 3D monitor for this OR staff also. Some advanced instruments are coming up, so I will tell later. This is the typical OT setup. for a SSI system. Docking is pretty similar. I just wanted to show this slide, this video, because when you insert the instrument, your assistant is continuously looking at the monitor, which has 3D visuals. So there are no chances that he is going to hit the tissues inside because he is also perceiving depth. These are few slides which I want to show that docking time is now pretty 5 to 6 minutes, except this one case with MBR, which took 16 minutes for docking. So vision with this 4K monitor is very nice. This video is just to show that how nicely it looks when, because this is 10x zoomed, and very nicely you can see all the small branches and do the dissection for IMA. Now our Lima takedown is around 40 to 50 minutes. 8 cases with bilateral IMA takedown. Now very good time, around 90 minutes. This TCAP was done in other hospital. I have borrowed this video from Dr. Sudhir Srivastava sir. He has done this case in Ahmedabad, just to show the use of stabilizer. Very nicely done anastomosis in this case. So the stabilizer is very good and it stabilizes very well. We have experimentally used stabilizer in our hospital without doing anastomosis to see how it is stabilizing. With the more experience of the system, we will try to do TCAPs in future. This is a small video to show ASD closer 3-port system with another assistant port. Very much stabilized system. You can do very precise dissection with the monopolar scissors also. This is a small video for mitral valve replacement, 4 ports and 3 centimeter assistant working port. Very densely calcified mitral. The instrument, this scissor, nicely cutting the valve. Very precise movement can be done without any difficulty. The stitching part also, if you see, very much stabilized, no tremors, no difficulty, no hiccups here. This was the case I was doing my first MBR. And very precise selection of the side to take the needle out can be done with the system. For the future development, they are coming up with the multi-fire clip pliers. They are coming up with the anastomotic connectors. And also they are developing on interrupted suturing clips or kind of suture system. So they are very much committed to the future development regarding cardiac surgery. Thank you so much.
And thank you for showing this nice technology and very nice procedures. Now we move to Europe, and we will hear about the intuitive Da Vinci system and also the CMA versus robot. And it is Joe Zacharias from Blackpool in the UK. That is not in the European Union, but it's in Europe.
Thank you, Gry. I appreciate actually a little bit ahead on my slides, apologies. Thank you for the invite, and I really do need to confess that I have not ever touched a patient with a robot, and so I feel very inadequate in this group, but I will talk to you quickly about the stuff that I've been fortunate enough to do. So I do have some conflicts of interest. The talk outline is primarily, I'm going to just start off by explaining my kind of passionate area, which is an idea of sub-xiphoid bilateral mammary harvesting. Then I'll talk to you about my experience with CMR, then my experience with single port, and what I feel could be potential steps. As you can see, the two mammaries lie probably about 4 to 5 centimeters around the sternum. They last 20 years if we get it right, but it just seems to be a real problem to get it down in more than, certainly in the UK, 2% of patients have a non-sternotomy approach, and only about 10% have bilateral mammaries. So we do have a problem where we're not using a very good conduit, and how do we make it easier? So it's now 29 years since the first port access CABG paper came out of the Stanford group. And that actually talked about taking the mammary down with an endoscope through the left side. And 29 years later, we still have very low uptake. And certainly, like I said, in the UK, it's 2%. I don't know how much it is in the US and in India and in other countries, but really it isn't as high a percentage as we want, or probably some of the robotic companies want either. Now, around the same time, endoscopic conduit harvesting came around. And as you can see, that took off very quickly. And certainly in America, it's 90+% penetration. And certainly in our practice in UK, again, it's very close to 90+%. And this obviously took off because, number one, it was simple. But number two, I do think taking conduits out in parallel is generally easier than taking conduits out perpendicularly, which is what we surgeons used to do with vein and radial artery. But going parallel simplifies it, and I do believe there is potential for it. Now, it's not a new idea. People have done this before. Haldun Karagöz from Turkey was one of the first who published a lot of it. And there's even some case series from Japan using robotics for it. So why subxiphoid? I think bilateral mammaries really are a very good conduit. I think, as Peter Sawalski says, if we separate the takedown of mammary arteries as conduit harvesting and the anastomosis is a separate operation, it may make sense to have it as two separate operations. And the most difficult part, as we all know, is taking the mammary down. The anastomosis sometimes is not that complicated. Now, we know that rib spaces are painful. We learned from thoracic surgery, who started with 3 ports, and now we're all trying to do it with 1 port. And the advantage of the subxiphoid is the endoscope can actually tell you where exactly the coronary arteries are, so your mini thoracotomy can be done much more accurately. And I think the subxiphoid space was a great place to put drains. So that's my background thing. We did try totally endoscopic. I won't go into details. It is quite difficult, and it's dependent on the shape of the sternum. I know the first few cases have been done in Serbia, and they were presented at the ISMIX meeting last year. Now, LSI has come out with some very clever gadgets to help, but I think the most useful thing will probably be the micro knot, which is going to be hopefully something of use for everybody. Now, I got involved with Cambridge Medical Robotics when one of my colleagues got me introduced to Mark Slack, who was the chief medical officer, and he kindly supported my option of trying to take mammaries down, and we managed to do it in 4 cadavers. We took down every mammary that is available. One of the cadavers actually had a lemur to LAD already done, so that is why we only got 7 mammaries. Now, we got very good length and very good caliber. We eventually worked out the best way to do it was to have the camera port subxiphoid, but the actual arms on either side. So we went subcostal, because otherwise there was a lot of clashing of the arms and it was not going as smoothly. As previous speakers have said, they come in consoles, and so they can be moved around, and they are very ergonomically easy to sort of sight. So this is a short video about one of the procedures that we did. So this is how we kind of positioned it. And as you can see, I think it's a spatula in one hand and a hook in the other. Now, I must confess that because I don't do much robotics, I was a little bit I often use one hand rather than both hands. And I notice very good robotic surgeons are kind of ambidextrous and go from one to the other. And this is something that I actually had to sort of learn with experience. I'm sure some of you on the panel would be a lot quicker with this. Now, the real advantage, as you can see, is the camera is 3D. You can push it forward, and you can just sort of put a hook over the lemur. And this is just basically dissecting it out. Obviously, in a cadaver, it's a lot easier, but sometimes in the cadaver, the hardest thing was actually trying to find the mammary. Now, we worked out that it's easier to start at the top and then work backwards initially, but later on, towards the end of our experience, we were able to start somewhere in the middle. And this is me coming backwards. It does get harder and harder as you get closer, because that is where a lot of our clashing was occurring. But going subcostal seemed to make a big difference, and it certainly helped us get less sort of instrument clashes and a smoother sort of ability to dissect stuff out. I do think coming nearer to the xiphoid is going to be the challenge, particularly with this approach and these sort of instruments. Now, what we found was that you probably don't need that much length, because with a closed sternum and talking to endoscopic surgeons, they generally stop at the 4th or the 5th space. Now, as you can see, the length of mammaries harvested were pretty decent. I have to thank Joel Dunning, who was supporting me through it all with his tremendous amount of thoracic robotic experience, and that was a team. Now, unfortunately, we had a big discussion with Mark Slack, who's in the middle, and the CMR group, but they were not happy to sort of support cardiac surgery. I think, like I said, the positive thing with CMR is the modular consoles, but it also can be a negative thing, because once you have more than 3, then there's very little space for an assistant. And so there may be potential issues with that sort of design. The instrument handling is very good, but like I said, I haven't used other platforms. Now, the real problem, according to Mark Slack, is that the venture capitalists who give them the money were very keen that they follow where people already are using robotics. So they were predominantly focusing on urology and gynecology and general surgery. So cardiac surgery was put as not a priority for the time being. Now, I was very impressed when I first saw the single port robot. As Pablo has shown, it's a very clever looking piece of engineering. And I was very fortunate to meet up with Gary Gutha, the CEO, who very kindly put me through to some of the other people in Intuitive. And we managed to get to Berlin. And Jörg Kempfert and myself did a lab in Berlin funded by Intuitive. Now, I'm aware that Hubert Stein and some Wokma and Michael Smith had done one earlier. But we managed to do bilateral mammary in a cadaver, and we also tried, I was quite keen to see what it was like to do something where there is actually blood flowing through arteries in case you kind of accidentally cut something, how we'd manage it. Now, I must say the bipolar diathermy and clips work very well. Obviously, it's Intuitive. They have 20 plus years of engineering behind them. And one of the nice things with the camera angle, and you'll see it in the video that I'm going to show you, is because it's not straight on, and a bit probably like the SSI, because there's an angle to it, it rarely got fogged up or bloodied, even when we had sort of some amount of bleeding. And of course, the instrument ergonomics with everything that Intuitive provides is very good and was excellent. Now, this bit of work that we did is about to be published in the interdisciplinary journal as an experimental study, and I'll play this video just for you to look at. So this is the SP. I mean, the nice thing is it's very easy to sight, and it was very quick to get in over the patient. As you can see, the camera has a sort of angle. And the other thing is the instruments, apart from having a wrist, they also have an elbow, which actually helps. Now, we decided to put a port in the sort of 4th space where we thought we would be doing the incision, and insufflated CO2 just to get the diaphragm out of the way. Now, this is something that the thoracic surgeons do a lot, to just be mindful of not damaging any of the abdominal organs. Now you can see there's a subcostal incision on the left side. Now we're just putting a soft tissue retractor through, and it's a small soft tissue retractor. And once it's sort of connected up, the Intuitive, small single access port gets connected. Now this is a beautiful piece of design where there's actually a kind of bubble with CO2 connected in it, and that increases the range of movement rather than once it's inside the chest. Now this is us just opening the mediastinum, so we open the pleura on both sides bilaterally, and initially we're just trying to get the reamer sort of dissected off. Now, as you can imagine, this is a cadaver. And so once we found the reamer, it's completely empty, but we're able to use a bipolar forceps and a spatula, and we managed to dissect the full length of the reamer. Now, because they are already very active in thoracic surgery, they do have these clips that are used to sort of clip off side branches. This is us using the bipolar diathermy to dissect some of the side branches. And then we also use these plastic clips just to trial it out. And they also work very well, to be fair. And of course, the nice thing with plastic clips is you don't have to worry about the diathermy going into the vessel. So this is all still coming from the left side, looking at the right, and you can see we're down at the bifurcation. We've flipped the two ends and divided the reamer. Once we divided the reamer, we moved, and as you can see, it's a very small movement, and you're straight onto the lemur. And this is one of the nice things about that sort of angle of attack, because it's just, I always say it's a bit like having two rail tracks, and you just go after one after the other. So here we're just using the bipolar diathermy to sort of see if we can divide the branch. Of course, it's a cadaver, so it doesn't bleed, but we're just kind of messing around. I do want to mention that both Jock Kempfert and me are not robotic surgeons, so if some of you think we're going very slow, it's probably because we'd only had about, well, this is, to be fair, this is the morning session with the cadaver, and then in the afternoon we had a session with the live pig hearts. So as you can see, we were able to get down to the bifurcation of the left as well, because we're coming from the subcostal area, there's quite good length. Now, once we put both the mammaries where we think we need them, we were able to sort of extend that little incision in the fourth space to create a mini thoracotomy. And these are the two mammaries that we pulled out. We kind of envisioned using the subxiphoid space for maybe either a sort of stabilizer if you're doing it off pump, or we could use some sort of thing like a sponge on a gauze. The nice thing is with the endoscope there, you can find the reamer and the OM and the LAD, and the plan was to put the lemur to the LAD and the reamer to the OM. So as you can see, it's potentially doable, certainly in a cadaver. We did have good time sort of doing it on a pig. The bleeding was, when we did have it, was easily controlled. The camera did not kind of get affected because of the angles. Now, what happens after BEMA harvest? Like I say, you can either do a Bonatti operation on pump or a bulky operation off pump, and it's up to people's preference. As we know, the randomized trials don't show a difference, so I think it's predominantly surgeon preference. And I think at some stage, if this becomes popular, there may be subcostal port instruments, but I don't think that will be happening soon. So in my own opinion, I've just made this graph up, so please, it's got no scientific basis, but it's just how I feel. Direct vision through mid-cav is probably low cost, but reasonable difficulty. Going endoscopic, which we have done, is slightly higher cost, but it's also more difficult. I found the CMR robot actually making it easier, but obviously additional cost. But I do think the single port robot was the easiest, and it was definitely the smoothest way to get two mammaries down quickly. And of course, the cost, I don't know what the cost is, but this month it's just been released in Europe and UK, so we will find the cost out soon. Now, I just want to bring this, if people are not aware of, it's called the ideal way of bringing in new technology. It's idea first, then development, then exploration, assessment, and a long-term study. And I do think if we are doing something like this, this would be the path to follow. And Johannes did say that humor is allowed in this webinar. So this slide is slightly kind of touching upon humor. I think what would be great would be to have a group called the Spartans. And we try and convince Intuitive to consider IMA harvesting as a non-cardiac procedure, because obviously we know trying to get cardiac is going to be very expensive for them. But I think IMA would come under thoracic, which they already have clearance for with all their robots. And maybe 10 centers do 10 cases each to prove feasibility. We then hopefully do a randomized control trial, publish it in the Lancet. And then I hope this will be a much easier and quicker and more reproducible way of getting surgeons to move away from doing sternotomies. And of course, we know if you go away from sternotomy, then mammary artery harvest is much less stressful because you don't have to worry about sternal wound infections. On that note, I think I'll stop. Thank you so much for waiting till the end for my talk, and please be in touch. And thank you once more for the invite.
Well, thank you very much for the great talk. We have to finish this session, unfortunately, because we cannot run over time. So Dr. Bonaros will say some closing words.
I think it was an amazing session. I was very impressed with the quality of the presentation. I was really very impressed that we all are aware now of the developments of robotic surgery. I think I would like to welcome you to learn more at the annual meeting of the ISMICS, which is going to be held in Athens at the end of May. And you're all welcome to meet us there and get in touch with the persons. I think Stan has the details here, and I will hand it to you, Stan.
Thank you, Dr. Benaros, and our entire faculty today, and everyone for joining us. And yes, as Dr. Benaros just said, the meeting in Athens is now 45 days away. So prepare for a wonderful meeting by ISMICS yet again in 24. Thank you all again, and this recording will be posted to the website within the next week. And again, we appreciate your participation today. If anyone has any other comments.
Thank you so much.
Thank you all.
Thank you.
Thanks, everyone.